So far, we have discussed that the existence of inertial frames, say S and S prime, and we are assuming that there is some transformation that takes us from S to S prime. And what we found is that if there is such a transformation, the intervals in one inertial frame, say ds, is going to be the interval in another inertial frame, ds prime. So now the question is, what is this transformation that takes us from S to S prime and vice versa? Well, it must be a transformation which has this property. So these transformations have a name after its inventor, and they are called the Lorenz Transformations. So this is our next topic. What are the Lorenz Transformations? So the Lorenz transformations are transformations which keep the intervals invariant. So if I have some interval, say S12, and this is given by sorry, this should be minus. Then the Lorentz transformations are transformations which take, the coordinates of, say, our two events. So these are coordinates, say, T1, X1, Y1, Z1, and say T2, X2, Y2, Z2. These transformations should take them to coordinates in a new reference frame, and the coordinates will be given by T1 prime, X1 prime, Y1 prime, Z1 prime, and this here will be given by T2 prime, X2 prime, Y2 prime, Z2 prime, but it'll take the interval S12 squared to the interval S12 prime squared in such a way that S12 is equal to S prime of 12. So this is what the Lorentz transformations are. We also want the transformations to be linear, because if it's not linear, then the transformations will not be one-to-one. Because if it's nonlinear, then we would be able to go from here to here, but going back, there will be some sort of ambiguity. So we want this to be linear. So because it's linear, we can express this transformation as a matrix. So to do so, let's introduce some notation. Let's introduce x mu to be the coordinates of some event. So x mu is a 4-tuple or 4 numbers, t, x, y, and z. So that means that x0 is going to be t, x1 is x, x2 is y, and x3 is z. So then x prime mu is going to be t prime, x prime, y prime, z prime. Now we can always choose our coordinate system such that what we were calling x1 of mu is just x of mu, meaning that x2 of mu is just a bunch of zeros. And x1 prime of mu is just x prime of mu, and that x2 prime of mu is just 0. We can write this as just 0. So we can do that And then we can write the linear transformation that we're looking for as x prime of mu. So this is, we can think of this as the mu index of a column matrix. And then we have a 4 by 4 matrix, which we are going to denote by lambda mu nu x nu. And there is a summation over nu, where nu goes from 0 to 3. So this is the linear transformation that we are looking for. This is just matrix multiplication. However, in relativity, it's customary to use a convention in which if some index is repeated, in this case nu, then we don't explicitly write the sum. The sum is there and it's implicitly understood, but we don't write this. So this equation becomes x prime of mu, lambda of mu nu, x of nu. And because there is a repeated sum, we assume that it is summed over. And of course, there is no nu on the left-hand side because it's summed over on the right-hand side. If this was not summed over on the right-hand side, there would be some sort of nu index on the left-hand side. So this is a linear transformation. So in this convention, where we write, we imply sum for repeated indices, is known as the Einstein convention. And Einstein called this the most useful invention of his life. So, before we can go on and describe what a Lorentz transformation really is, or what are the properties of these matrices, we need to introduce another type of index, the downstairs index. So before we do that, we introduce a rank 2 tensor, and this is called the metric tensor. So this is a tensor with 16 components because each of these indices go from 0 to 3. So there are 4 possibilities. So this guy has 16 components, but it's a very special tensor. And if we write it as a matrix, which we can do because it's got 2 indices, then this tensor has in its diagonal 0, 0 component 1. Its 1, 1 component is -1. Its 2, 2 component is -1, and its 3, 3 component is -1. All the other components of this tensor is 0, are 0. So in other words, this is 1, otherwise it's 0. So what this metric tensor does is that it allows us to define something which has a downstairs index. So we can define x downstairs of mu as eta mu nu x of nu. So of course there is an implied summation. But because most of the components of eta are 0, there is actually very little summing over happening here. So we can then look at eta, and then it's easy to see that x with downstairs 0 is going to be equal to x with upstairs 0, but x with downstairs 1 will be minus x with upstairs 1. X with downstairs 2 will be equal to minus of x with upstairs 2. X with downstairs 3 is going to be equal to x with minus x with upstairs 3. So the Lorentz transformation says that if I take some coordinate of an event x mu and then make a transformation to a new inertial reference frame, then the coordinate of that point becomes x prime of mu but that's related to X through a linear transformation, which is given by this lambda matrix, X of nu. And so what happens to X downstairs of mu? So X downstairs of mu, what it does is that it transforms in the following way. X prime downstairs of mu becomes the same Lorentz transformation matrix, but the downstairs index is now mu, and the upstairs index is nu, and this is X prime and nu. And this can be derived from this guy and the fact that eta is a tensor. What does that mean? That means that under a Lorentz transformation, eta transforms as eta prime mu nu, and then this is gamma sigma of mu, gamma rho of nu times eta sigma rho. Now note that this is the row and this is the column. This is the row, this is the column. So this is basically what is meant by a tensor. A tensor of rank 2 transforms like this. This is the definition of a tensor. Now, one of the things about tensor or vector is that if it's 0 in one coordinate system, it's 0 in every coordinate system. And therefore, the fact that we chose x 2 mu to be 0 in one coordinate system means that x2 prime of mu in another coordinate system is lambda mu nu x2 of nu, but all of these guys are 0, therefore this is 0 as well. So something that transforms in a tensorial way is if it's 0 in one reference frame, it's 0 in any other reference frame. Okay, so what are we trying to say here? Let's get back. What we want to show is that if we have some interval, say ds, say 1, 2 in one reference frame, it's equal to the ds1, 2 in another reference frame. But what is what is s1, 2 in our first reference frame? Well, it's actually x mu downstairs, x mu upstairs. If you don't believe me, let's go and look at this. This is going to be given by x0 squared. And here we see there's a minus sign here, here, and here. That means this will be giving us minus x1 squared minus x2 squared minus x3 squared, right? And this is just t squared minus x squared minus y squared minus z squared. This is exactly what we meant by the interval. Of course, here we are saying that x2 mu is 0. So according to special relativity, this thing will be equal to s prime of 1, 2 squared, which is x prime of mu, x prime of mu. So this thing, let's look at what this is. This is x prime of mu downstairs, x prime of mu upstairs. But x prime of mu downstairs can be written as eta mu rho, x prime of rho upstairs, x prime of mu upstairs. And then we can write eta mu rho. Here we have Lorentz transformation matrix with rho and say alpha x of alpha, and here we have mu and beta x of beta. So this has to be equal to s of 1, 2 squared, but s of 1, 2 squared is just say x mu. Of course, this index is summed over, so it's a dummy index. So what this means is that eta mu rho, gamma rho, lambda rho alpha, lambda mu of beta, this whole thing times x of alpha, x of beta, this means that this better be eta of alpha beta, x alpha, x beta. Because if that is the case, then we will have x downstairs alpha, x upstairs alpha, and then this is equal to what we are calling S12 squared. So in other words, the interval being invariant implies that the Lorentz transformation matrices must satisfy this relationship. Mu nu, lambda, say mu, lambda nu, alpha, beta is equal to eta, alpha, beta. So this is the transformation that they have to satisfy. Now, what we can do is that we can now introduce the transpose matrix of lambda to be, so this is the transpose and this is the mu row and the new column, and that is given by lambda nu mu. So if I do this, then I can write this as a matrix equation. And let's just rearrange everything. So we have lambda mu alpha, eta mu nu, lambda nu beta is equals to eta alpha beta. But the first thing is the transpose of alpha mu, eta mu nu, lambda nu beta, eta alpha beta. So we can write this in matrix form as the transpose of the Lorentz transformation matrix applying on the eta matrix times another Lorentz transformation matrix is equal to eta. So this is the condition that the Lorentz transformation matrices have to satisfy. So these are, this is actually a generalization of what the rotation matrices have to satisfy. You remember that rotation matrices in 3 dimensions are orthogonal matrices, and they satisfy our transpose R is equal to the identity matrix. We can write this as R transpose times the identity times R is equal to 1. So what we see is that for Lorentz transformation, the role of the identity matrix is taken over by the metric tensor. So matrices, the Lorentz transformation matrices, they are called orthogonal matrix, and they form a group or all the Lorentz transformation matrices together are called O for orthogonal 1, 3. The 1, 3 stands for the fact that the metric tensor eta mu nu has a diagonal, along its diagonal, 1 plus 1 and 3 minus 1s. So this is called the signature of our metric tensor.